Hello everyone, my name is Harnit, Assistant Professor in Ajay Kumar Garg Engineering College. Today the topic of discussion is graphs, isomorphism and homomorphism. Right? First of all, we should know what is a graph. A graph is determined as a mathematical structure that represents a particular function by connecting a set of points. It is used to create a pairwise relationship between objects. The graph is made up of vertices, which are called nodes also, and they are connected by the edges, that is called lines. Now, if there is some graph where we have vertices, right? And there is an edge between that vertices. That means this vertex and this vertex, there is some relation between that two vertices. These are nodes. They can represent anything according to the problem. And if they have a relation between them, then there is an edge between them. Right? What are isomorphic graphs? The isomorphism graph can be described as a graph in which a single graph can have more than one form, right? There are different ways to draw the same graph, right? If the number of edges or the connections are same, that means the graphs are isomorphic graphs. That means two different graphs can have same number of edges, vertices, and same edge connectivity. Then they are isomorphic graphs. Now you can see here, if we have three vertices, right? A, B, C, right? We have relation A to B, B to C, and C to A. Suppose, right? We can draw this way also. A, B, C. A, C, and B. We can draw this way, right? Now, again, there is a relation between A to B, then we can make A to B. Relation between A to C, A to C. Relation between C to B, then C to B again. Right? This can be drawn like this also. A, B, C. Right? Relation is there between A to B, B to C, and C to A. Right? This can be drawn this way also. A, C, B. A to B there is a relation. A to C there is a relation. C to B there is a relation. Right? So all these are isomorphic graphs because the number of vertices are same and the edges between these vertices are also same. Okay, we can draw a graph in number of ways, but the number of vertices and edges and the edge connectivity should not change. Then they are isomorphic graphs. Now see here. Now let's have the technical definition. In graph theory, the isomorphism of graphs G and H is a bijection between the vertex sets of G and H such that any two vertices U and V of G are adjacent in G if and only if Fu and Fy means are adjacent. Now you can see here. Here you can check out this graph. There is a blue vertex. Blue is connected to green vertex. Green is connected to red vertex. And red is connected to black type of vertex, right? And there is an edge between light blue and red also, right? Now you can see this graph. Blue to green, there is an edge, okay, right? There is an edge from blue to red, there is an edge. Then blue to green we have already drawn. Green to red, right? Blue to blue, blue to dark blue, blue to orange, right? All the edges are covered here. All these edges are there. And there is no extra edge in this and no extra vertex in this. Right? These two are isomorphic graphs. Now similarly, you can check here. We have four vertices. Green to blue, green to orange, orange to dark blue, orange to dark blue, light blue to dark blue, light blue to dark blue, blue to orange, blue to orange, right? You can draw the edge anyway, in any up, down, anywhere, right? But these two graphs are isomorphic graphs. Now, first of all, you should know the properties. While checking for the isomorphic graphs, what all you should check? There should be equal number of vertices in both the graphs, equal number of edges in both the graphs, equal number of vertices with the same degree, vertex correspondence and edge correspondence should be same, right? Now see here, let's take this example. We have two graphs, we have to check whether these two graphs are isomorphic or not. Now first step was the number of vertices should be same in both the graphs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 vertices in both the graphs. Then edges should be same. 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6. Oh, we have counted this as 2 times. 1, 2, 3, 4, 5 and 6. Both the graphs have same number of edges, right? 6 edges. Now we have to note down the degrees. What is the degree of A? 3. It is connected to 3 edges are connecting to it. So that is why A is having 3 degrees. D 2 degree, E 2, C also 2, B 3. Right? Similarly here 3 has 2 degree, 1 has 3 degree, 2 is also having 3 degree, 5 is having 2 degree, 4 is having 2 degree. Right? Now let's see how we will map. In this graph, A is equal to 3, B is equal to 3, C is equal to 2, D is equal to 2, E is equal to 2, and here 1 is equal to 3, 2 is equal to 3, 3 is equal to 2, 4 is equal to 2, 5 is equal to 2, right? Now you check. There are 2 3 degree vertices, 3 degree vertices, okay? 3 2 degree vertices, 3 2 degree vertices, right? Now we have to map all these vertices to each other to see that whether they are making the same graph or not. Now A or B can be mapped to 1, A can be mapped to 2, A can be mapped to, B can be also mapped to 1 or 2, right? There can be any combinations, more than 1 combinations, you have to try all. But the edge sequencing should be same in both the graphs. Now let's say we map A with F1, right? If we map A with 1, B with 2, C with 3, D with 4 and E with 5, right? Here also you can take any combination, but you have to check whether they are forming the same graph or not. Now see, A is mapped to 1, right? Now here A is connected to C and A is connected to D. A is connected to C and A is connected to D. Similarly, 1 should be connected to 3 and 1 should be connected to, see here, A is connected to D, B and C. D is mapped with 4 and B is mapped with 2, C is mapped with 3. So A is connected to D, B, C. So 1 should be connected to 2, 3, 4. See here, 1 should be connected to 2, 3 and 4. It is okay, right? Whatever we have done the mapping here, that the vertex which we have mapped with the other vertex, there are same connections in this. Check it again, right? This first we are checking the A vertex, right? A vertex is connected to C, connected to B, connected to D. Instead of D, we can write, D is mapped to 4, we can write here 4. There should be a connection between 1 and 4. 1 and 4, there is a connection, right? Similarly, A is connected to B. A is 1 and B is mapped to 3. B is mapped to 2, sorry. B is mapped to 2. That means 1 is connected to 2. Yes, 1 should be connected to 2. A is mapped with 3. Sorry, A is connected to C. A is 1, C is 3. There should be edge between 1 and 3. 1 and 3, there is an edge. See here. Right? That means it is okay. This combination is okay. Similarly, come to D now. Right? Check this for all the vertices. D is connected to A. That means 4 is connected to 1. 4 is connected to 1. Then D is connected to E. E is what? E is mapped to 5. This is 5. Right? 4 is connected to 5. There should be an edge between 4 and 1 and 4 and 5. 4 and 1, there should be edge. Yes, it is there. 4 and 5, there should be an edge. Yes, there is there. This combination is also okay. Then comes to this vertex now. Right? B is what? 2. 2 is connected to 1. 2 is connected to 1. Or you can say B is connected to A. B is connected to E. Yani 2 is connected to 5. B is connected to C. 2 is connected to 3. Right? We have done the mapping line. There should be edge between 2 and 1. 2 and 1, there is an edge. 2 and 5. 2 and 5, there is an edge. 2 and 3, there is an edge. 2 and 3, there is an edge. Right? This combination is also okay. Now let's check for C. C again, we have already checked this. There is an edge between C and A, C and B. That means 1 and 2, 1 and 3, there should be an edge, and 2 and 3, there should be an edge. Right? 1 and 2, 2 and 3, there is an edge. Okay. This is also okay. We are left with E vertex now. E vertex is connected to D. Means 5 is connected to 4. 5 and E is connected to B. 5 should be connected to 2. Right? 5 should be connected to 2. 5 should be connected to 4. Yes, this combination is also, this mapping is also okay. That means these two are isomorphic graphs. Right? Let's take another example. Again, we have to do the same thing. For this, you can try any combination and then check every vertex that whether the connections are same or not. See here, A is mapped to 1, B is mapped to 6, C is mapped to 8, D is mapped to 3, J is mapped to 7, I is mapped to 4, H is mapped to 2. This mapping is done and G is mapped to 5, right? Now let's check it out. A is connected to G, A is connected to H, A is connected to I, right? Now, blue is connected to G, blue is connected to green, blue is connected to green, right? Blue is connected to red, blue is connected to red, yes. Blue is connected to I, yani this peach color, then blue is connected to 4, right? That means this mapping is okay. Then check for another vertex G. G to A means green to blue, green to blue, green to pink, green to pink, green to light green, green to light green. Again, this connection is okay. Check for this vertex. Pink, pink to light red, pink to light red, pink to purple, pink to purple, then pink to green, right? Again, this mapping is okay. Similarly, check for H. H is connected to B, pink 1. There is an H. H is connected to D, means red to blue. Here, there is an H. Then H is connected to blue. Then here it is connected, right? Similarly, you can check for all the vertices, right? This is again a bipartite graph. Sorry, isomorphic graph. Now, another example. A is mapped with 6 because the degrees are same here. This is also 3 degree. This is also 3 degree. This is 1, 2, 3, 4 degrees. You have to map it with 4 degree only. This here, the 4 degrees is this, right? F is having 1, 2, 3, 4 degree. Then F has to be mapped with 4 degree vertex. This is also this. Purple one, this is also having 4. Then this is mapped with this vertex, right? This is also having the same degree. E is having 4. Again, this is having this one. And C is having 3 degree. Then this 3 is also having 3 degree, right? This mapping is done. Now let's check. A is connected to, means red vertex is connected to yellow, red and yellow, red and light red, red and light red, then red to purple, right? These all edges are there. Now let's check for this one, yellow vertex. Yellow is connected to red, light red, green and light green, right? Yellow is here. It is connected to red, yes. Light red, yes. Then green, yes. Light green, yes, right? This vertex, this is connected to yellow. Then this vertex you have to check. It is connected to yellow, yes. Then light green, green. Then purple, then 3 degree. We have completed all the edges. So similarly, you can do for D, F and E. You will find that the connections are same. So they are isomorphic graphs. Now again, these vertices, again you can check what the mapping is done. A to 1, B to 2, C to 3, D to 4 and E to 5. Check it out. A is connected to D, B, C, right? Means A is 1, B is 2, C is 3, D is 4 and E is 5, right? Now 1 is connected. There should be an edge between 1 and 4, 1 and 4, 1 and 2, 1 and 2, 1 and 3, 1 and 3, right? Check for D. 4 and 1, 4 and 5. 4 and 1, 4 and 5, right? 4 and 5, okay. Now check for this one. 2 is connected to 1, 5 and 3. 2 is connected to 1, 5 and 3. Check for C. It means 3 is connected to 1 and 2. 3 is connected to 1 and 2, right? Check for this vertex. 5 is connected to 4. 5 is connected to 2. 5 is connected to 4. 5 is connected to 2. This way it is an isomorphic graph. Now you can test whether it is a isomorphic graph or not. How you will check? First you will check the vertices 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Number of vertices are same. Number of edges 1, 2, 3, 4, 5, 6, 7. Right? You check here also. 1, 2, 3, 4, 5, 6, 7. Right? Number of edges are also same. Now check the degree. 2, 1, 2, 3, 4, 4, 1, 2, 2, 3, 0, 3. Right? Here 1, 2, 1, 1, 2, 3, 4, 5, 2, 3. You can check that degrees of vertices are not same. Here we are having a 0 degree vertex. Here there is no 0 degree vertex. There is a 1 degree vertex here, but here there is no 1 degree vertex. So this way, these are the reasons why these two graphs are not isomorphic graphs. Now comes the homomorphic graphs. Two graphs G1 and G2 are said to be homomorphic if each of these graphs can be obtained from the same graph by dividing some of the edges G with more vertices, right? Means there's a small graph, we can extend that graph by adding vertices edges to it, or we can decrease that graph by decreasing the vertices and edges, right? A homomorphism that forms between the simple graph G1 to the simple graph G2 is a mapping. Here also we can do a mapping, but there cannot be one-to-one mapping because number of vertices and edges are maybe not same in these graphs, right? Now see, you can check this graph. We are having a shape like this, and we are having 1, 2, 3, 4, 5, 6, 7, 8 and 9 vertices here. If we delete this vertex and this vertex, right? See here, we get this graph, right? Similarly, this graph can be obtained if we delete these also. Then these are all homomorphic graphs. But here you can say that the shape is same, but the number of vertices and edges are different. We are just, if we go from this side, we have this minimum graph. We are adding some of the vertices here, and here we obtain this graph, right? Here you can add these vertices, you can obtain this graph. Then you can add more vertices to it, we can get this graph, right? Similarly, if we get this way, we can delete some of the vertices, we get this graph. More deletion, get this graph, right? So one graph can be obtained from the other graph. So that type of graphs are called homomorphic graphs. Now, check whether these two graphs are homomorphic or not, right? We can see the shape here. This, this and this. This is same here. Okay, need not to worry about this. We are having this edge, right? This edge, if we take one vertex here, we can obtain this edge, right? This edge, here there is a vertex, here there is a vertex, here there is a vertex. I'm talking about this. Or we draw this edge like this or this. These are the same graphs, right? So this edge is pulled here and one vertex is added to it, right? If we add this vertex, then this shape and this shape is same. That means the shape is same, and these are the homomorphic graphs, right? Now we check these graphs. This shape is same. There is one edge here, there is one edge here. So need not to worry about this. Now what we have done, we have to check this. What we have done, we have pulled this edge and added one vertex here, right? So again, this can be this, right? Or this way. See, when we have pulled this edge can be made like this. Okay, this edge can be made like this, right? We have this vertex is there, already there. Then these are also homomorphic graphs. Now the properties of the homomorphic graphs. When you are testing both the graphs are homomorphic or not, homomorphism always retains the graph's edges and connectedness, right? If there is a connection between the two vertices, then while there will be a connection between those vertices directly or indirectly in the homomorphic graph. If homomorphism is a bijective mapping, then it is isomorphism. If we are able to map every vertex with a unique vertex there, right, in both the graphs, then that homomorphic, and then they are isomorphic also, right? The compositions of homomorphism are also homomorphism. Finding out if there is any homomorphic graph or the another graph is an NP complete problem. Thank you.